In this video, we're going to be talking about logistic growth. And this is actually an equation that you find in a lot of Algebra 2 and even pre-calculus textbooks. But teachers skip over it because I think they're kind of scared of it. And when I first taught it in BC, I was a little nervous teaching it. But it's actually a really, really cool equation. And it has a lot of practical applications for us. So, what a logistic equation is here we have the exponential growth model that we did a few days ago. Now, if you have a carrying capacity of your population, so like if you're looking at a habitat of wolves, for example, I think we do a wolves problem. And that population has a certain capacity. There's a certain amount of wolves that they can have in their property. It's called the limiting factor, the carrying capacity, which is the amount of wolves I can have. And we have this limiting factor here. Now, this equation here is the one that our old book used. I want you to be familiar with it. The one that you see more often is the one that this book uses, which is that. What they did is they just factored out the L, and that L gets carried into this K that's out here. These K's are two different K's, just so you know, because I factored it out. So this is a logistic differential equation, and the logistic curve, the solution to this differential equation, looks something like this, where I have an initial condition, and I go up, and then about here, halfway to my carrying capacity, I'm increasing the fastest, and then I start slowing down and get to my carrying capacity. Okay? So let's do an example with this. I think it's going to make more sense once we do an example. And I'm recording this for my fall 2020 classes. If we were in class, we would actually do an activity where we would discover this equation on its own. So I apologize. We can't do that activity, but I hope to be able to do this in future years. That activity in future years. Okay, so the growth rate of a population of mountain goats in a newly established wildlife preserve is modeled by this differential equation, where T is measured in years. So I kept this the same from the old book, because even our new book uses this. So what I'm going to do is I'm going to put this in terms of our new book. The one that I see more often on the AP I didn't want to do that. I'm going to multiply the 30 to the 0.008 just so that you all can recognize that this equation here is the same as this equation here. Okay? Okay, so from here, what is the carrying capacity? So you just have to look at the equation and determine what the carrying capacity is. It's this number in the denominator, 30 goats. So that means that there's a maximum of 30 goats that this wildlife preserve can sustain. What is the goat population when the population is growing the fastest? So that's at the inflection point. And what we'll do in class is we'll graph this. And I want to show you guys that this happens at 30 over 2, or half the comparing capacity, so 15 goats. And then for part C, what is the rate of change of the goat population when it is growing the fastest? So remember, this is a P, 15 is P, so I plug into my dP dt because that's a rate of change. And I use my calculator and I solve that, and I get 1.8. Now this is what a slope field for that differential equation looks like. So they notice how it kind of goes up and then goes to, it goes up, 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 and then evens out. So if there's 3 male, 3 female, so 6 total are introduced when we start, sketch the number of goats. So I know it is really hard to see, but there's my 6. That's my initial condition. And then I go up pretty steeply. And then we finally even out. Notice what happens here at about 15. 15's about right here. Is that's where it's the steepest, and then I start to even out. Notice how 30 here is a horizontal asymptote. Okay, so keep that in mind, because that was the carrying capacity of our wildlife preserve. Now what I'm going to do here is we're going to use separation of variables, and we're going to solve our equation. I am going to use this one. Because it's a little bit easier. So I'm going to separate my variables. Now you need to use integration by partial fractions to simplify this. I will tell you that A and B are both 30. You're welcome to find those, but I won't have enough space on my screen if I try and find those. So you're welcome to find those. It's actually 1 over 30. So when I integrate, I get 1 over 30 integral of 1 over P plus 1 over 30 minus P dp is equal to, I'm going to integrate this. I'm just going to leave it unintegrated. I'm going to integrate both sides at the same time. I was going to integrate one side, but I'm not going to quite yet. Okay, so 1 over 30 ln of P minus, because of this minus sign in here, and that's in a quantity, ln of 30 minus P is equal to 0.008 T plus C. So simplifying this out, I'm going to take, and I'm going to multiply both sides by 30. So I get 0.24 T plus C. Now notice how that is that value there. Okay, so everything's kind of related. I'm going to combine these into one logarithm. And no, I didn't forget my absolute value signs this time. Our population is growing. So our population here, P, if I plug in 6, I'm going to get positive numbers. So leaving it like that. Now what I'm going to do is I'm going to take this, I'm going to continue up here, and I'm going to do e to the 0.24 t with a big C in front is equal to P over 30 minus P. Now I'm going to use my initial condition. So now I'm going to use my initial condition of 0, 6, and I get K to be, not K, in my notes it's K. Here, it is the number C. So we get that equation. Now, if I were to solve that equation for P, I'm not going to go through that algebra with you guys because one, I'm going to run out of room. I wish I had my big board on here. We get this equation. So now that equation, I'm going to simplify it and put it into a form that a lot of the books use. I'm going to multiply by this. It actually makes it a little bit easier on us. So I get 30 on the top. This term here turns to a 1 plus a 4 e to the negative 0.24 t. Okay, so that is now our regular equation. So if I were to graph this equation, that would look something like this equation. Actually, I want you guys to graph that for me. Confirm that my slope field, or the curve that I drew in, actually matches this curve. Remember, you probably have to adjust your window a little bit. So now we have the solution to a general logistic differential equation. So I have this as my logistic equation, and this now is your regular function that came out of this problem, out of this differential equation. L and K are positive constants, L is the carrying capacity, and B is determined by my initial condition. Okay? You want to memorize these. Quite honestly, I haven't seen the regular equation a whole lot on the AP. The one that I do see is this equation. So I would make sure you know that. And that is, as a spoiler alert, a question that does show up a lot of times on those quick quizzes that I like to give second semester. Okay, my second example here. A population of rabbits in a large field is given by that formula, where T is the number of months after rabbits were released. Determine the maximum number of rabbits that the field can maintain. So I need to find my carrying capacity. So I go back to my equation. Carrying capacity is found up there. So my carrying capacity is 1,000. Now find the value of K. So this right there is equal to negative 1,000, my carrying capacity, times by whatever K is. It's not T, Mrs. Marnell. So then to solve for K, I get, and I feel like I've done this wrong, and I think I have incorrect things in my notes, so I do have a incorrect in my notes. 0.0007. Okay. What is the population when T equals 0? Okay, that's just plugging T equals 0. That goes to 1. So I have 1,000 divided by that. I just find that in my calculator. I get 8.163. So that's like my initial condition of rabbits. Okay. Now, what is the population when the rate of growth is the greatest? So that's saying when does the second derivative have a maximum? And remember that always happens at half of the carrying capacity. So that's 500. Part E, use your calculator to determine the population found in part D. So you set our equation that they gave us, 500 equals what was it, 1,000 over 1 plus 121.51 e to the negative 0.7t. Do I have that right? Yes. So again, what I would do, we have our calculators, put that in y2, put that in y1, and find the intersection. And that happens at 6.857. And remember, we're going to be talking about this in terms of 3 decimal places. Give me time, number of months. Okay, the last equation, or last problem, I should say. So the rate at which the number of moves in a section of a game is given by that function where t is in years. And let's use this equation now. So, because I want you guys to have an example where you're using this equation. So if 4 moves are introduced into the new habitat, what will be the maximum number of moves the habitat will support? So what's the carrying capacity? In this equation, the carrying capacity is found right there. So 40 is my carrying capacity. What will the rate at which the moose population is growing the greatest? That's at half the carrying capacity. That's 20. Now, part C is a really good question, and part C got me for years because I didn't fully understand logistic growth, but I think now after my 3rd year, it's my 3rd year teaching it, I think I have a much better handle on it. A well-meaning but misinformed person suggests that by introducing 50 moose initially, there will be more moose available to hunt. Why is this faulty reasoning? Because the carrying capacity is 40. You're introducing more moose than the habitat can hold. So what's going to happen is actually in your logistic curve, I wish I had more room. So if that's 40, which is what, if you introduce less than 40, your curve goes up to that. But if you introduce more than 40, what happens, say I'm up here at 50, my curve goes down to 40. Okay, so the carrying capacity is 40. We can't have more than 40. 40 is the ideal for this habitat. Okay, so that is logistic growth. I think it's a really cool application of differential equations that we've been doing. It is a guaranteed question on the AP test, at least in multiple choice, but I have seen it in free response in a few years, and I have seen it kind of recently in free response too.